Welcome you all to this course on diffraction and imaging. In the last class, we discussed about one-dimensional lattice. Okay, what are the types of symmetry which are associated with one-dimensional lattice? Okay, both point group as well as the space groups we considered. Right, there are 5 point groups and total 7 space groups are possible for a non-dimensional lattice. Today we will look at 2-dimensional lattices. Okay. What all types of rotation which was possible in one-dimensional lattice? Only two-fold rotation, right? And we also considered that we can have one-fold, two-fold, three-fold, 4 and 6-fold rotation are the rotations which are possible for 2-dimensional lattice, but this is true for 3-dimensional lattice also. These are all the types of rotations which are consistent with translational periodicity, right. In addition to it, we have mirror, correct, and these are all the independent operations which are possible. Okay. If we have a material which exhibits a 4-fold rotation, what all other symmetry elements which are possible? 2-fold and 1-fold is possible, correct? Is it not? Whereas for 1-fold there is only 1-fold rotation is possible. That means that it is not only the 4-fold rotation, these are also possible, right? You consider 6-fold. Then what all rotations which are possible? 6-fold, 3-fold, 2-fold and 1-fold. All these operations are possible, correct? So that means that the group of operations which are possible for a 6-fold is that contains all these symmetry elements. So like that we can consider various symmetry elements. Okay. We can consider combination of these symmetry elements. If we consider the combination of these symmetry elements, okay, in 2-fold, what all which we can have? 1-fold and mirror, 2-fold and mirror, 4-fold and mirror, okay, 6-fold and mirror, right. These are all the combinations which we can choose, is it not? That 6 independent rotation symmetry are there, then a mirror is there. We can have a combination also in 2-dimensional lattice. If we take that, these are all the possibilities which are going to be there. This 1-fold and mirror will turn out to be what? Only a mirror, okay. Then this is another one, okay. So essentially if we add now, how many symmetry elements are there? 10. So essentially we can have 10 2-dimensional point group symmetries, crystallographic point group symmetries are possible, correct? This one can easily work out, that is what I wanted to tell, okay. It is not very difficult. Okay. And in a 2-dimensional lattice, if we consider it, this 1-fold, okay, is essentially, if we take an asymmetric motif, because the easiest way in which we can do it is take a motif which does not have any periodicity associated with it, okay. Like if we consider, okay, I will take P. If we take this is an asymmetric motif which it could be a molecule, okay, but which does not have any symmetry associated with it. Then only symmetry which it can have is only a 1-fold rotation, correct. There can be a case where the molecule itself has got one, there is another one if we consider it, then what is the symmetry which this has? So this has got only a mirror symmetry which is associated with it, correct. So like this, knowing the symmetry operation, one can construct the various types of motifs which are possible, correct. That is what we discussed in the last class also, okay. So, essentially these sort of motifs itself also could be used to keep it on a point. So, these are all motif around a point, correct? That is around some axis we are seeing that these are all the rotational symmetries which are possible. Then if rotation and a mirror is also there, here the mirror is parallel to the axis of rotation, correct, in all these cases. Okay. So, then we can have, these are all the possibilities which exist. Okay. So, essentially 10 planar point group symmetries are possible. Okay. Then I also mentioned that this can be described in different forms or on different ways represented. The way in which it can be represented is, one is using the symbols, Hermann-Maguire symbol or the Schoenfly symbol. Another is with a stereographic projection we can represent it. Okay. Then there is a matrix representation, in which what is the type of matrix which you use to transform from one coordinates of one point to a coordinate of another point. Okay. Or physically we can draw the picture itself and do this representation. All the representations have been used, okay, in crystallography. Okay. Here what I am trying to do is to show the, for two dimensional lattice, okay, how it is represented in a stereographic projection. You remember the stereographic projection? Okay. Essentially assume that this is a sphere, okay, and the coordinates x, y is in, and when we are viewing from here, okay, the pole of any point here, okay, on the surface, it will be cutting, if you view it from here, cutting along a particular point, okay, on the equatorial plane, correct? In a two dimensional lattice what happens? The Z information is not there, correct? So, we are keeping, essentially you assume that we are keeping a lattice right at the equatorial plane. Okay. How do we construct the pole? There what we, the pole is nothing but a plane normal. Here what will be the plane? That is, if this is the all the row of atoms which are there in one dimension, okay, to which we will be drawing a normal, correct? So, various, we can draw the normals, they will all be meeting on which plane? On the equatorial plane, correct? The projection when we see it in 3 dimension, projection when we see it in 2 dimension, it is essentially the poles are lying on the circumference of the equatorial plane, correct? Because of that, for a 2-dimensional stereographic projection, for any point which we want to represent is essentially represented at the circumference of the circle. Whereas, in a 3 dimension, for a pole which is going to be here, its representation will be within that inside. So, this is the difference which one should notice it. Here if you see it, okay, a projection which is being shown, okay, this is the axis which is being shown, okay, on the 2-dimensional projection. If we take a pole of one point, okay, this will be rotated by 180 degree for 2-fold rotation, it will come here. This is one way to represent. Another way in which it is represented is on the same stereographic projection, the symbol used for 2-fold rotation is nothing but an ellipse. That way also we can represent it. Okay. Here I am considering a case for a mirror. Okay. There what the mirror is perpendicular to placed on y axis, that is along the y axis it is lying y. So, then what is going to happen, if we have any point on the circumference, this point will be represented here. Suppose this is for a 3-dimensional crystal, possibly what may happen is that instead of this point may come inside and its reflection will come inside. That we will come to later. But this subtle difference, one should know that for two-dimensional lattices, all the poles which we show are going to be on the circumference. Okay. Similarly, we can do it for a, and not only that, with a thick line in the stereographic projection, the mirror will be represented. Okay. This way also one can represent it. For 2 mm if we consider, okay, we take a pole, rotate it 180 degree, it comes here, another rotation it comes back, right. And if we take a mirror along, keep a mirror on the YZ plane, then what is going to happen is that this will get reflected here, this point will get reflected here. Okay. So, now we have 4 poles are going to be there. This represents 2 mm symmetry on a stereogram. Okay. That is what essentially is being shown here by, and once a mirror has been kept and this sort of poles have been generated, we can immediately see that it is equivalent to putting a mirror on the XZ plane as well. So, that is why here you see that the symbols which are used is twofold is with ellipse and 2 mirrors are being shown. Okay. This you can see it, this is for 4 mm. Okay. In addition to it, there is some other information which is also being provided. Okay. That I will come to later after I essentially what is being done is that if you have a crystal with this symmetry, okay, because all this point group symmetry has been found out by looking at material, looking at the external forms. Okay. What are the types of shapes which can give rise to the same type of a shapes can be external shape, if you look at it, can be different, but still the same symmetry can be exhibited. For example, tetrahedron, what is the symmetry? It belongs to a cubic, correct? You take a cube, if a crystal goes into a shape, that also will have a cubic symmetry, but if you look at the shape, they have a different shape, correct? Tetrahedron is not the same as a cube, but both can exhibit the same symmetry. So, this what is being shown is what are the types of surfaces which it can have, what is the symmetry associated with it. That information is also given in these tables. Okay. So, essentially what we have is that in a 2-dimensional lattice, if we consider the point group symmetries which we can have are only 10, correct? Now, let us look at some symmetries associated with the 2-dimensional lattice, because we have looked at only the point group symmetry, correct? That is around a point which we have considered, which is consistent with the periodicity of the lattice. Okay. So, here what I have done is we are taking a rectangular lattice. Okay. In this rectangular lattice, by inspection, looking at it, what are symmetries which it can have? Twofold, where it can be there, because once we fix a lattice, where we can have the symmetry is also fixed, correct? So, one, we can have a twofold here, that is on any of the lattice points we can have, right? Because we are only just showing a part of the lattice, lattice is an infinite one, correct? So, we can have a twofold symmetry around all the lattice points. Is there any other place where we can have a twofold symmetry, any other symmetry? That is, if I take a point here, or here, or here, or here, all these points also I can have a twofold symmetry, na? Is it not? If I take an axis here, at this particular point, rotate the lattice by 180 degree, all these points will come back to original position, identical position. Again rotate it once more, it will come back to original position. That means that this point also has got a two-fold symmetry, correct? So now two-fold symmetry is there like this here. Points are there. In addition to it, if I take this point, okay, around this point also, if I give an 180 degree rotation around this point, then also it will be coming back to an identical position. So here also we have two-dimensional, that is two-fold symmetry is there, correct? So these are all the points which we have two-fold symmetry. Okay. What is it which is there other than this? If I see with respect to a plane like this, we have a mirror symmetry. A plane like this, if we take a mirror symmetry, okay, correct? So that's also going to be there. So we have a two-fold and a mirror symmetry, and this is generally represented as P 2 mm. That's how it is. And we say that for a crystal having this sort of a symmetry, A equals B, A not equal to B, that angle between them is 90 degree, correct? This is exactly what we are showing, only a one unit cell. Okay, what are the symmetry elements which are associated with it?
Mirror two centers also.
Mirror?
Two centers.
That's here. Yeah. Okay. Okay. These are all the symmetry elements which you have. Okay. Mirror and the symmetry elements are there. Is it not? Okay. And if you look at any lattice point, what are symmetries which are associated with it now here? This has, okay, one two-fold. Okay. These are all the symmetry elements which are associated with it. Mirror. Okay. This is exactly what the point group symmetry also, right? What we have looked at it, point group symmetry around a point, okay, is this corresponds to 2 mm, correct? So here if we look at all these points, all of them exhibit the same type of a symmetry, correct? 2 mm. And any point which is there here, the center here, if we consider it, what will be the symmetry which it will exhibit? Only an one-fold rotation symmetry, because around this point, except for 360 degree rotation around this axis, okay, any other rotation it will not come back to identical position. Okay. From consideration of this lattice, you can immediately understand that apart from the lattice points which are having an identical symmetry, there are other points in the material which also exhibit some symmetry elements associated with it. Okay. These types of points are called as special points, okay, in the crystals, the unit cell of the crystal. Okay. Now let us consider a square lattice. In a square lattice, what all types of symmetry which we can have here? Four-fold symmetry is possible. So that means that four-fold symmetry, the symbol is just putting a square to represent it. Okay. I am just showing one unit cell. This is four-fold. By looking at this, is there any other symmetry elements which are possible at any other place? Here twofold will come, here twofold will come, okay, and here also again at the center you will have a fourfold, correct? Then in addition to it you will have a mirror symmetry which will come passing through this, correct? Is it not? Then along the diagonals, correct? Okay. So if you now look at any of these points, you have a fourfold, these are all the symmetry elements which are there, correct? This is essentially for four mm symmetry, okay, point group symmetry, it's going to be 4 mm. For a 4 mm symmetry, if you look at it, this is the symbol which we use, right? Point groups, planar point groups, these are all the two mirror planes which are cutting each other. So that is exactly what we have. Okay. In addition to that, if I consider an axis like this, okay, here what happens, suppose we assume that on these points, okay, an atom is being placed or an motif with an infinite symmetry is being placed, okay, then what is it which is going to happen? Okay. That is, if I put a plane like this, okay, a mirror plane like this, what it will happen is that this will be reflected and it should come here, but there is nothing is going to be there. But if from here to here, what is the distance? It is a by root 2 with respect to the, if a is the side of the unit cell, then from here to here you shift it, and then around this if you take a reflection, this point will be generated, correct? So this is nothing but, and again from here to here you shift it by half the lattice translation vector in this direction, and again take a reflection around it, you get it. This is what we have discussed earlier, that this is nothing but a glide, correct? So in addition to mirror, okay, a glide also is inherently there in this one. It is not separately added, okay, but the structure has got glide also present in it, okay. So if we look at all the points, okay, that is, this is the unit cell which we are considering it here, okay, what are the symmetry elements which are associated with it? Around any of these lattice points we have a 4 mm symmetry. Around this point we have 4 mm symmetry, correct? Then around this point 2 mm symmetry. Similarly, we have here 2 mm symmetry is there. Then there is a mirror, there is a glide, one fold symmetry, all these symmetries except for that one fold, there are some symmetry element or the other is present, okay. What I wanted to remember here is that we talked with respect to 10 point groups, okay, what are the types of symmetries which can be associated with it, okay. Here also if we look at it, that same type of a symmetry element is being associated with it. If I take that motif like 4 mm symmetry, if I take it R, it will be okay. I will just put it with a circle, okay. That means that there will be, just to represent that one of the points, that is at anywhere if I put it for a 4 mm symmetry, around this there should be 8 equivalent points should be there, then only the 4 mm symmetry will be satisfied. this you assume it represents an asymmetric motif. Okay. Is it clear? Okay. If I take this and put it here, then what will happen? With respect to the lattice, the motif which I have chosen, all its symmetry elements match perfectly, correct? Then only this putting one motif at that point is good enough to satisfy the full symmetry of the lattice. Is it clear? See, this could as well be this is a 8-sided one. Yeah, 8-sided one. Suppose this is the motif symmetry. Okay. If I take it and keep it here at this point, okay, the same symmetry is being, all the symmetry elements match. If the symmetry elements match with this one motif, keeping it there at the lattice point, the lattice could be generated. Is this clear? Suppose I keep the motif in such a way, okay, that instead of keeping it here, suppose I keep this motif somewhere here, then what will happen? Because I am putting at a point where it is one fold, then at 8 positions around that it has to be kept. Even though it has the full symmetry, it has to be kept to satisfy the complete symmetry. You understand that? That is a point which I want to emphasize. So, the point where we keep it, what are symmetry elements which are associated with it? We have to look at it, okay, and whether the symmetry elements match or not, or also has to be seen. Is this clear? Okay. So, essentially in this structure, if you look at it, we have many positions are there, okay, where we could place, because this is a lattice. In this lattice, atom could be kept at the lattice points or at this middle of this, each of these lattice translation vector sites, or at the center of the unit cell, or at any point here. So, there are many possibilities, or on these mirror planes we could keep it, okay. Anywhere we can keep it and create a lattice, 2-dimensional. The same is true for 3-dimensional lattice also. Okay. Okay. Before going into it, those details further, what I have done it is that just shown that this is the way we can find out the symmetry of the lattices. Okay. So, for the 5 2-dimensional lattices, the symmetries which are associated with it, okay, the representation, because this is C-centered, so it is 2 mm, others are all, and this is the maximum symmetry a crystal can exhibit, because around each lattice point, suppose we put an atom, and we generally assume atom to be spherical. If an atom is spherical, one single atom if we put it, then since it has got infinite symmetry associated with it, okay, all the lattice, the symmetry around each of the lattice point or the sites is satisfied by that, okay. Because of that, the maximum, the symmetry which the crystal will exhibit is this particular one. But depending upon the shape, okay, it can exhibit symmetries which are less than this also. Okay. In fact, these are all the types of symbols which we use for 3-fold, 4-fold, then 6-fold. Okay. And in this another one also which we should consider it is that if you look at the factors of 4, the 4 is 4 into 1, right, 2 into 2 it will come, 4 can come, okay. And here similarly if you look at 6, 6, 3, 2, 1, okay. So these are all the groups which you can see, okay. So if a crystal is having a 6-fold symmetry, or what are the symmetry lower than that which it can have, okay, they are also given by this root. That is, a 6-fold crystal can exhibit a 3-fold symmetry. What can happen is that when a phase transformation takes place, okay, from one structure to another structure, when it undergoes a transformation, phase transformation or transition, you can, physics you call it as a phase transition, okay, then there is a relationship between what sort of structures which it can form when it goes from one structure to another structure, okay. What is very important is that from this, between 4-fold and 6-fold, that is between cubic or cubic and hexagonal, if you look at it, there is nothing common between them, okay. These are two different classes of structures. That is, in a cubic structure, in a cube, okay, by whichever way you arrange atoms around the lattice point, you can't create a hexagonal lattice. In a hexagonal lattice, whichever way you try to put motifs around them, you can't create a lattice with a cubic symmetry. You understand that? Is this clear? This you might have noticed in many of these phase transformations when you are studying. You might not have been aware of it, that why it happens, but this is because of this reason. It is related to the symmetry. Here what I have considered is that let us take a different type of motifs, okay. No, different type of a two-dimensional lattice, put a motif around it. This is a parallelogram, oblique lattice, and what is the symmetry which is associated with it? It has 2-fold symmetry which is associated with this lattice, correct? What is the symmetry of the lattice? 2-fold, right? That is, if I that is around this point, if I around this axis, if I do an 180-degree rotation, I will be able to bring it back, correct? This has got a 2-fold rotation. But around each lattice point, around it I am putting an asymmetric motif. When an asymmetric motif has been placed, okay, then at the identical position we have to place the motif. So when we do that, now if you look at this crystal, what is the symmetry which it has? Only an 1-fold symmetry, right? The 2-fold symmetry is lost, okay. And here you see that it is essentially a rectangular lattice, where when we keep a motif, asymmetric motif, okay, only 1-fold symmetry is present, right, P1. So this is what essentially it happens with all, irrespective of, though the lattice has got a higher symmetry, the symmetry of the motif also decides. So not only the symmetry of the motif, if a symmetry has got an infinite, if the motif has got an infinite symmetry associated with it, then it can exhibit the complete symmetry of the lattice. If the motif has got a symmetry which is higher than that of the lattice, and depending upon how the different axes of symmetry match, that decides what is going to be the symmetry that which is common to them, between both of them, that group, that decides the symmetry of the crystal. Is it clear? Like here what I have done it is, similarly I have taken a motif which has got a 4-fold symmetry, right. So if you look at this motif, it has got a 4-fold symmetry associated with it around this axis, if I take it rotational symmetry, right. This lattice is essentially a oblique lattice which has got only a 2-fold symmetry. when I keep this around it, okay, since the axis of rotation, the fourfold as well as the twofold, because when I say it as a fourfold, it has got a twofold rotation also associated with it. So, the which is common to them both is the twofold. So, this exhibits now a twofold rotation, and like here it is essentially a rectangular one, where when I put a fourfold again around each of this lattice point, it is essentially a twofold rotation is what the lattice has got, and motif has got a fourfold rotation and the twofold rotation. Since the axis coincide, it will exhibit only a twofold, right. Whereas here if we see it, it is a square lattice around which I am putting a motif which has got a fourfold rotation. Okay. Now this exhibits the fourfold symmetry, correct? Is this clear? But you should understand that this exhibits only a fourfold symmetry. What is the symmetry of this lattice, square lattice generally? 4 mm. But that mirror is, do you see that? No, mirror is not there. That is because the mirror planes of the lattice, okay, is there, but this has got no mirror symmetry associated with it. You understand that? Okay. I am just taking it a few examples to illustrate the point. Here if you see it, okay, I have taken the same type of a lattice. Okay. It is oblique lattice, two-dimensional lattice, into which I am taking only an asymmetric motif and keeping it here. Though it has a twofold rotation, now it becomes as if it has got only one-fold rotation, correct? Now you look here, it has a twofold rotation associated with it, the motif which has been kept, and the axis of that motif which has been put, twofold rotation axis, and that of the lattice, they match, correct? So, because of that the crystal exhibits twofold, correct? And here it is a twofold onto which a motif with a fourfold symmetry is kept, but still what it will exhibit is only the twofold symmetry. Here it is, I am putting a threefold around a twofold, because the lattice has got a twofold symmetry. Okay. I put a motif which has got a threefold symmetry, but the axis of the motif match, but between 2 and 3 there is nothing common in that symmetry elements. Because of that, this will exhibit now only a non-fold. You understand that? So, what you have looked at it is crystals, okay, and lattices we have looked at it. What are the symmetries which are associated with the lattice we have discussed, and depending upon the symmetry of the motif which we place it, okay, what all associated, what all symmetry elements which are common, not only they are common, which are matching with the symmetry elements at a specific point where we are putting that motif, that is going to decide what will be the symmetry which the crystal will exhibit. Is this clear? This is the bottom line of this entire discussion so far. If you look at the International Union of Crystallography table, okay, the way these various two-dimensional point groups are represented, okay, when we try to put motifs around each of these point, okay, one, it will be just showing what is the unit cell shape, okay, this is how it is going to be, this is for P1, okay, and we are putting a motif at one point. That to represent a motif, this is just the symbol which is being used, circle is a symbol which is being used to represent a motif, okay. If we keep it at any particular point, at an identical position we keep it, okay. This is how this is the crystal which it will be there. This is called as a general point, that where we put it, the motif which does not contain any symmetry, that point is called as the general point. And here at this lattice, if we see, these are all the symmetry elements which are associated with it. But we are essentially putting motive at one particular point. So, correspondingly one will come here by 180-degree rotation. Okay. This is how exactly the general point which is going to be there. If you look within this unit cell, always two motifs are going to be there, correct? Is it not? Because this also will satisfy a twofold rotation. Okay. Similarly, if you take a mirror which is going to be there on one axis, okay. If you take here, since the mirror is only one single mirror is there, okay. Essentially this symbol which is being used, that is circle with a comma inside, that is what the International Crystallography table they use it, that represents that it's a mirror image. Okay. So, this is how it will be done. What is essentially interesting is that here there is a mirror is there, that mirror image when we take it, if we give a glide also, that is half a translation, okay, bring it, then what will happen? For this point the mirror image will come here, correct? Because what is being done is that you take it from here, translate it and then take a mirror, then translate it, take a mirror, okay. Then this type of structures can also exist. Is this clear? Okay. Essentially what we do, you assume that the mirror is here, okay. So, for this point the mirror is this is how it is, this is PM, just a mirror is there, correct? If the same structure this dashed line if you use is to represent the glide plane. Okay. Now, if you see it in this structure, what we have done it from here to here is the lattice translation vector, correct? We have shifted it by half and then take a mirror image, again shifted it by half, that is translated by half distance and then taken a mirror image. So, it will come back to this position. Okay. This type of structures are also possible in crystal structures. Okay. So, this is another type of, like this, in addition to mirror, the glide also gets added to it, then the number of two-dimensional groups which we can have turns out to be 17. Okay. That is where you can see that only wherever somewhere mirrors are there, mirrors also get in some cases the glide is inherently a part of the mirror, then we do not continue. In some cases the glide can be generated, like in this particular case. Okay. This type of crystal structures are also there. Many of the molecules have this type of structures are there. Okay. So, essentially if you look at it, this you can go through it later through these slides, okay, or the books which I have mentioned where these structures are explained in detail. Okay. But generally in those books, this is the graphical representation. One is the symmetry which is represented on the unit cell, another is the position of the asymmetric motif or around each lattice point is represented, that is called as a general position. Okay. These are all the two things which are represented. And in addition to it, another information which is important is that if we have to construct a crystal structure, a two-dimensional structure, if we go from what are the coordinates when we do the symmetry operations for any particular how it transforms, that information is also required, correct? Okay. that information is given, also given in the International Union of Crystallography. Like here what happens is that you see that this is oblique lattice, 2-dimensional lattice, only asymmetric motif is kept at any particular point, okay. And what is being given is that something called as a Wyckoff position, that is the symmetry associated with this one fold, okay, and the coordinates are just xy, okay. To this, what will be the coordinate of this one? By a lattice translation operation, if we do it in this direction, you will be adding by 1 0 0, if you add you will be getting it. In this one, 0 1 0, like that in any direction, 1 1 if we add in this direction, like that we can find out what will be the coordinates at which the motifs have to be placed, that we can find out, okay. Like here if you see it, this is a square lattice, okay. In this square lattice we have a 4-fold rotation is there, okay, and a 2-fold is there, but there is no mirror, okay. So what all points which we have? There is one point here which has a 4 mm symmetry. I had shown just some time back that in this point has got a 4 mm symmetry. This point also has got 4 mm symmetry, correct. This point has got 2 mm symmetry, correct. So that is what is being shown. That is, if you see one, what is essentially is being shown is that the 4-fold symmetry. That means that if I keep an atom at this position 0 0, okay, by lattice translation the atoms at all other points could be generated, okay. That is essentially what is being shown here. The multiplicity is 1 here, okay. And if you see at the middle also I can put 1, then also it will satisfy the full symmetry of the lattice, correct. That is another point. Instead of putting an atom at this point, I can consider a square lattice, infinite lattice, put atoms at these points at the center of that lattice points, then also it will exhibit the same symmetry of the lattice will be exhibited, crystals can have, okay. Or I can put it at this point, okay. If I do that, the positions where I can do it is half 0, okay, that is in this case x is half, y 0, similarly 0 half, in this it can be done. In these 2 points also if I put, they will also exhibit the 4-fold symmetry, right. And then general point, anywhere you put it, not at any of the special lattice points, if you put an atom, then also the 4-fold symmetry will be satisfied, okay. That is, if we have an atom, okay, this is the lattice which is there, what are the various ways in which, or what are the various positions where we can put the atom and still satisfy the symmetry of this particular crystal. This itself is, I am showing it in another way, like this is 1, I put it around 0 0 by lattice translation vector, okay. Next one will come at the another lattice point, all lattice points we have to keep an atom, right. And if you look at these ones, these 4 ones, do they satisfy a 4-fold symmetry? They satisfy a 4-fold symmetry, correct. If I put one at the center here instead of putting it there, and like that one will come here, another will come here, another will come here, all the lattices, then also a 4-fold symmetry is satisfied. You look here, put at these 2 positions by taking the lattice translation symmetry, one point will be generated here, another will be generated. Though this is the lattice which we considered, atoms are put at these positions. Now this also has a 4-fold symmetry, correct. So that way also we can fill up the lattice. And this is where we are putting an atom at a position which does not have any symmetry associated with it. Then we have to keep it like this. Then you can see that this also satisfies a 4-fold symmetry. But what is the difference which you see between all these? Here the number of lattice points per unit cell is 1. Here also the number of lattice points, the number of atoms per unit cell is 1 here. here the number of atoms per unit cell is 1. What happens here? 2. Here 4. Okay. So depending upon where you put it, the number of atoms which will be required to generate the specific lattice changes, and that is dictated by the symmetry which is associated with it. Okay. The points which have got the maximum symmetry of the lattice, the fourfold symmetry, then we require only one. Okay. That is what the multiplicity in this table which we represent it gives, and here the multiplicity is 2. Okay. In a general, one shows the full maximum number of atoms which will be required if you put it at the general point to create the lattice. But all the way we are creating a crystal, okay, by all these methods, okay, the various methods which I have adopted, we are generating a crystal, but it is having a symmetry which is that same, right? Crystal has got the same symmetry. If you have any questions, you please do stop me and ask me. Okay, that's very important. Okay, and that is what essentially is represented. Now, in these ones, what is being given? The coordinates of each of these points. If we take x, y, okay, it will turn out to be minus y x, then minus x minus y, y minus x. This is going to be the coordinates. If these are all the coordinates of the points for a general transformation, we can find out the matrix which is responsible for it also. We can relate it. That way also we can represent the lattice translation. Okay, we can represent the symmetry. Okay, there are many methods of representation, but this table is very important, because if you understand this table and how the structures come, this could be utilized to construct any crystal structure. That is what we use from International Union of Crystallography table, okay, to generate different type of to generate and draw different type of crystal structures. Is it clear? Here I have taken, this is the lattice symmetry is 4 mm. Okay. Now I am taking a one with a 4 mm symmetry, right. Here if you look at it, a mirror is also attached to it, each of the lattice point here. Now the number of special points, that is these points which have got some symmetry associated with it, they are called as special points. Okay. Each point has got some called as a site symmetry, right. What is site symmetry is, at this particular site it has a 4 mm symmetry, at this particular site it has a 2 mm symmetry, because with respect to neighbors, if you try to look at it positions where they are, what is the symmetry which it shows, that is called as the site symmetry. That is what is being, that site symmetry is also a subgroup of the main symmetry element of the lattice. Okay. Is this clear? Okay. And in addition to it, they give also for the different type of values, what are the conditions under which the reflections will be absent or present. All those conditions are also mentioned in this table itself. This table is a very useful, this contains lot of other information, okay, crystallographic, but to construct a crystal structure, this particular table which gives the coordinates and the Wyckoff positions of the various special and general point is what is really necessary. Is this clear? Okay. So if we do that, we will have totally around 17 planar point groups are going to be there. Okay. Now we have come to an end. So what I have done it is that when we say P1 one-fold symmetry, actually it has to be written P111, because along x-axis one-fold symmetry, y-axis is one-fold symmetry, z-axis is one-fold symmetry, because we use some coordinate system to represent it, right. With respect to that, but generally a short symbol is used to represent as P1. Okay. This also I had given. This is taken from the book and Hammond's book, that using R as an asymmetric one, then what the type of what are the types of crystals which can be constructed, two-dimensional crystals with different space groups. we can have distinctly only 17, which is possible. Okay. This is also another way in which that same thing is being represented. This is taken from the Kelly and Knowles book. Okay, one can go through this and understand it. Okay. Essentially all are the same. Only in this case of 3M, there are two positions are there, that is 3M1 and 31M. This I will not discuss about all these finer details, because I just wanted to give you a flavor of how to what are the types of symmetries which are associated with it. Okay. How this can be used to construct the various types of lattices and understand, because the aim of doing X-ray diffraction or electron diffraction or neutron diffraction, one of the main aim is to find out the crystal structure, for which looking at the symmetry of the pattern, which is especially the two-dimensional pattern, is what we get it, and how to go about, and for which one should understand the symmetries which are associated with the lattice. It is very much necessary. Okay. Earlier people used to work on mostly metallic systems. Now it is not just metallurgy, it is on material science, where people work on all types of ferroelectric materials, okay, piezoelectric materials, various types of photonic materials, okay, where they have different types of crystal structures are there, okay, and people are doing extensively electron microscopy. So one should be able to looking at the diffraction pattern, one should be able, and all diffraction patterns are two-dimensional patterns. So the types of symmetries which it can exhibit, these are all the types of symmetries, and these are all the 5 types of two-dimensional lattices which it can form. Okay. What I will do is I will stop here. Okay. It is already time. You will have class now, right? Some of you have class is there. Okay. Stop here. In the next class we will from most of the information which is necessary has been told. Then we will talk about what are the other additional symmetry elements which are necessary for a space lattice. Okay. That we will consider. Okay. We will stop here now.